Hey guys, so this is example 7. This should be on your pink pickup, day 2 of 3 for section 3.3, related rates. So I've drawn the picture here, but I'm going to go ahead and do it again just so you can see exactly what I did. And we're going to take this one step at a time like we always do. A camera is mounted 3,000 feet from the space shuttle launching pad. Okay, so I'm just going to choose to draw a space shuttle launching pad. I don't really know what they look like, but that's fine. And then it says a camera is mounted 3,000 feet from that. Okay, so let's just draw it this way. It doesn't really matter which way you draw it. And here's the camera. This is some epically awesome camera by NASA, right? And then this is 3,000 feet. Cool. Okay. All right. The camera needs to pivot as the shuttle is launched. So let's say that this is a shuttle, right? Now, as this launches, okay, this camera needs to pivot. That makes sense, right? Because it wants to follow the launch. If the shuttle is rising vertically, so this shuttle is rising up, right? Okay. At some rate, when it is 4,000 feet high, how fast is the camera to shuttle distance changing? Well, you'd imagine that as the shuttle rises, right? Eventually it's going to be somewhere up here. And then the camera to shuttle distance is going to be this right here, okay, that D. And I'm going to call it D. I don't care what variables you use. It doesn't matter. So since it doesn't matter, I'm just going to use Y for this height, okay? And now what you can see we've created, and we always like to start with this, is a triangle, right? And yes, it is a right triangle, okay? So that's going to be helpful for us. And then, as always, what are we given in math language? We want to write what we're given in math language. So if we have the 3,000 feet, wonderful, okay? If the camera shuttle is rising vertically at 800 feet per second, okay, rising vertically. So this is rising, right? Which means that this is what is changing, the height of this, which makes sense because the shuttle is increasing in height, okay? Which means that we are finding the change of y with respect to time. So dy dt, right, with respect to time. And we know that that's 800 feet per second. And then it says, when it is 4,000 feet high. Well, this is the height, right? So that's just saying once it reaches 4,000 feet, y is 4,000 feet, okay? And then the next step here, always write what we are looking to find, okay? And it says, how fast is the camera to shuttle distance changing? That word changing, we should immediately be thinking the derivative, okay? So we want to know at what rate is this distance here changing with respect to time, okay? And so mathematically, we write dd dt, right? And that's what we're looking for. And then our last step here is writing our equations. And there's really only one equation we have to relate all these things together, and that's going to be, let's call this x squared for now, plus y squared equals d squared, right? But in our last example, example 6, with the ladder, right, we knew that the ladder was a constant distance. So when we took the derivative, we got 0. So we may as well save ourselves some time here and say, well, x is always going to be 3,000, this x. It's never going to change because the distance from the shuttle to the camera, neither of those things are moving, the launch pad and the camera, which means that instead of writing x squared, I'm just going to go ahead and save us some time and write 3,000 squared, okay, plus y squared equals d squared, because that's going to save us some time when we take the derivative, which, since we're looking for d dt, we do have to take the derivative of this, right? And so the derivative of 3,000 squared, that's just a number. It's going to be 0. The derivative of y squared is 2y, but with respect to time, so dy dt, that's going to equal, again, the derivative of d squared is 2d, but with respect to time, d dt. Okay? And so we know we're looking for this. We don't have d yet, but we can find it, right? We have dy dt, and we have y. Okay, so we can solve this, but before we do that, let's just get our y variable, or sorry, our d variable. We know that in this problem, we have a y value of 4,000, and so what we've just done is do 4,000, 3,000, and then d, so we can find our d by the Pythagorean theorem, 3,000 squared plus 4,000 squared equals d squared. Well, this is a 3, 4, 5 it looks like. So d is in fact going to be 5,000. Okay. And so knowing that, we can use our formula here to find our missing variable. So I'm going to ignore the 0 because it doesn't really matter and just focus on this. 2 times y, our y value is 4,000, right? Okay. Times our dy dt, which was given to us, 800, is going to be equal to 2 times d, which we found to be 5,000, and d dt is what we're looking for. Okay. Now you can simplify all this however you want. I just see that these 2's are going to cancel, but if you want to multiply it out and then divide, I'm totally fine with that. But eventually what you're going to get is, 4,000 times 800 all divided by 5,000, right? And so if you go do that out and you can simplify it, you'll get 640 feet per second. Awesome. Okay, great. I'm going to pause it so you guys can take a second, digest, and then I'll go through the next part of this problem.